In this course, we'll continue our conversation into what USD is and how we author it using Solaris. Some of the topics that we'll cover in this course include bringing USD files into Solaris, layering USD to create scenes, and analysis of what's happening inside of the USD files themselves. Our goal for this course is to build a strong foundation of USD concepts in Solaris in order for you to be able to build scenes and workflows. For the first chapter in this course, let's take a look at the two most basic ways of importing USD into Solaris, and that's the sublayer and reference nodes. So here we are in the Houdini user interface, and we've got a demo file loaded that comes along with this course. So the first part of this that we're going to take a look at is in this sublayer and reference box. So what we're going to be doing here is taking one simple scene that's created in this gray subnetwork here, and we're going to be loading it in and looking at how we can load that file from disk. Now what we've got here is just a really simple scene built up with some geometry, shaders, camera, some lights, and then some render settings. So first of all, let's take a look at the sublayer node. So this node will just bring in the entire scene that we have on disk here in this node and that we've written out. It'll just bring it in exactly the way that we wrote this hierarchy to disk. So if we look over here, we can see that we have all of these different elements coming in pretty much exactly the same as they were in this gray node here. So if we look at this, there's 5 top level primitives. Over here, we have 5 top level primitives, and we can open those up and take a look at all those different elements inside of there. This scene graph tree pane is very similar to the outliner that you would find in Maya or the scene graph that you would find in Katana. However, in this instance, you can't drag and drop things within the actual pane. You need a separate node to be able to do that, and a little later in our stage manager chapter, we'll talk about that. So sublayer, you can see right here, is just referencing the simple scene.usd, and it's just bringing in everything that's in there. There's no way of telling it what to do with these files or anything like that from a hierarchy standpoint. It just brings it right into the scene. The one thing that we can do here is we can bring in multiple files. So if we needed to add another file into here, we could sublayer another file into our scene. So that's a possibility here. But other than just bringing everything in that file into the stage, there's not much we can do there. If we want more specific control, that's where the reference node comes in. So in the reference here, we're looking at that exact same scene, our simple scene.usd. And I should just note that if you don't have that written out to disk yet, we should click on this right here and just make sure it's saved to disk. And that will make sure that we're loading these pieces of geometry in properly. But so this simple scene.usd is being brought in here. And if we look at our scene graph tree over here on the left, we can see that it's just making one primitive that's called simple scene, and the ground and sphere geo are being brought into it. So that's obviously a lot more specific than we were looking at in our sublayer node. So let's kind of just break down what's going on in the reference node parameters here, and then we can kind of understand a little bit better what this node is used for. So the first thing we see here is the primitive path. And basically what that's saying is when we load the objects in this reference node, where are we going to put those things? So what we're using here is source name, and that's basically just taking the simple scene part of this and stripping off the extension and just calling it simple scene. So that is creating a reference to the name of our USD file that we're bringing in. Now we're only doing one primitive count here. We're referencing this as a reference file. We could also do it as a payload, or we could do some other things from this secondary input here as well. But for right now, we'll just use reference file. We'll talk about what those other elements are a little bit later on in this course. So we come down a little bit further and we see this here that says reference primitive. And this is referencing an automatically chosen primitive within that USD file. So if we wanted to bring in a different part of this scene, because as we could see, there's a bunch of different sections here. So it can only bring in like one branch of this hierarchical tree. It can only bring one in at a time. So what we could do here is we could now reference a specific primitive, and now we have this down here. So obviously we don't have a real clear way of seeing what's in our scene, and so we can click on this and now it'll bring up everything that's within that USD file on disk. And so if we wanted to say bring the lights in instead, we could hit apply, and now when we zoom out we can see that we have our lights in our scene, and there's obviously a dome light, and that's creating this background here. We could select something else like maybe the camera if we just wanted to bring that in, and there's our green camera that we brought in. So this primitive reference right here is what allows us to be able to kind of say what part of this branch, this branching hierarchy, do we want to bring in. Unfortunately, you can't select just the top level of this branch. You do have to select one of these primitives. So that's where this really differentiates between a sublayer. So this also gives you the opportunity to bring in multiple references as well. So you could technically bring in the same USD file here. So we've got our simple scene. We could just copy that, paste that down here, and we could bring in the camera. And now we have the geometry coming in as well. We could also here select something like the lights, for example, and now we have our camera and our lights. So we could reference all these things in and kind of build up our scene that way. But as you can see here, this is starting to kind of create some hierarchy issues. We're loading them all into the same top level primitive here called simple scene. So you have to be kind of careful with this, and maybe bringing it in this way might not exactly be the best way of doing this, but it just gives you an understanding of what a reference node is doing versus the sublayer and how those both bring in USD files from disk. So let's now talk about the asset reference LOP and how that allows us to bring USD assets from disk onto our stage in Solaris. So here we are in the asset reference section of this demo file, and we're looking at two nodes here. One of them is going to create this asset, and the other one is going to read it from disk. So this subnetwork here has a bunch of the component builder nodes that we've created within Solaris to kind of create these variants and elements and things like that we build into an asset. This isn't something we're going to get into in this section of this course, but it will be something we get to in a later part of this learning path. So you can always dissect this and see what's going on in here, but just know that there's some different geometries and different texture variations being saved on this asset demo file. And so if we go into here and just make sure we hit save to disk, it's going to write everything out to disk that we need to be able to just kind of see what's happening when we try to load this information back in. So if someone was to give you, an asset that has variations on it, whether it be geometry variants or material variants, the asset reference would be what we would use to load that in and be able to specify those things. So it's very similar to the way that the standard reference node works. We have our reference file right here that we're reading from disk. And up here we have a destination primitive $OS, which is reading out and the name of this node here, which is demo asset, and putting it into the top level primitive that's created here. So we can see in our demo asset create, we kind of have a little bit of hierarchy going on here, and we can specify what part of that hierarchy we want to load in if we want to. So here we can say reference primitive, reference specific primitive, and we can control click on this and open up our hierarchy and see. So maybe we just want to bring in the render geometry. That'd be fine. That's only going to bring in just that render geometry from disk. Now, there's reasons you might want to do that. There's reasons you might want to do something slightly different from loading it in, but just to know that you have that option, that does strip out some of the data that is built in an asset with variants. But in this case, you might want to do that for some reason. So I'm just going to set this back to where it was, so it loads all those variants and all that stuff back in. The other thing we can see up at the top here is that we can set the primitive kind, which in this case is a component. You could set it to be a group or an assembly, but usually those are for, multiple components either put together into a group or multiple groups are put into an assembly. So it's kind of a hierarchy of what the primitive is. So that kind of goes from finest level to coarsest level in this order here. And then again, we can set the parent primitive type, just like we've talked about previously, either to be XForm and have transformation data or scope with no transformation data. In this instance, we have an unanimated asset, and therefore having the transform would obviously be a helpful thing to have. Now, if you were bringing in something like an animated character that's in place in the scene right where you want them, you might want to keep it with a scope so that it doesn't accidentally get transformed away from that location that you've placed it at. And that also then leads to this tab. We can set any transformation that we want to on this primitive as it comes in. So that's a little bit different than what we were seeing before in the sublayer and the reference. And then this last tab here is going to allow us to bring in a variant, for example. let's say we wanted to group that in a different place when we set this variant. What we could do up here on this destination primitive is we could say something like variant 1. And we could actually have this be grouped into a separate section like this. So now that adds another primitive here. So anytime you see this destination primitive, just know that you can add a path in front of this $OS or whatever your kind of root level primitive, and it will add that primitive above it. So in this case, we have variant 1, demo asset, and then inside all of the things that we need to create this asset. So now let's make this variant. So we can add in a number of variants, and really just all this is just something to know that if someone has given you an asset like this, this is how you can import it. This isn't showing you how to set those variants. That's done in this subnetwork, and we'll get to in a later course. But just for now, just know that you could set something like a geometry variant and grab something like the rubber toy that's set in there, or the Tommy. You've got all these different geometries that are in there. And then we could also grab another variant set, which is the material variant set. And we could do something like, I don't know, like the wax or like a red velvet. And that's going to load in those things from disk. So this is kind of the way that you would bring in something that's given to you as an asset, maybe with multiple variants, multiple geometries on it, and allow you to bring that in a controlled manner into your scene in Solaris. Payloads are a special type of reference in USD. They allow for us to unload assets from our viewport in order to optimize performance and focus on specific parts of our scene. First of all, let's talk about what exactly is a payload. So a payload is just a special type of reference that can be unloaded from our scene in order to optimize our performance. And another thing about it is that it has a weaker opinion. Basically what that means is that when we load a payload into our scene, and if we try to overwrite something in our scene with a payload, and it's a reference or a sublayer, it's not going to override properly because its strength is weaker than those other primitives in the scene. So what does it mean when we unload a payload? So when we're unloading these payloads, basically the stage in our USD scene won't load anything in the file being payloaded. So that just means that it's going to look through our USD file when it gets to a file that's payloaded. If we have those turned off or unloaded in the scene, it won't look at anything inside of that file. So then you might say, well, how could you know what's in there if you're working on a scene? Well, what we can do is write a lightweight description of the contents, and those are like asset info, variants, the bounding box, in order to know what's not being loaded particularly into the scene, like what the geometry is that we're missing. You'll see that in a moment when we start unloading things, but just know that we can add that description to a primitive above where it's getting referenced, and it'll be able to show you those contents in the viewer. So let's just look at this as just like a little visual to understand what's going on here. So in this case, we have our payload, which is this yellow car, is loaded in the scene, which is basically our white truck here. And when we want to do something like unload it, you'll see here, we now have a reference of where that object would be, but it's just a bounding box. It's just something to show us what would be there if we loaded it. And also you can see that the car's kind of unloaded its springs, and it's definitely a lot lighter right now. And that is just kind of showing like, hey, this is a lighter scene. So when we have it loaded, everything's kind of weighed down. We have a lot of things going on in the viewport. When we unload it, we actually get some performance benefit, but we still know more or less the shape of what the object is that would be in that place. Before we get into unloading in the viewport, I just want to look at how these assets were built so that we can understand a little bit more about what's going on when we unload them. So what we're loading here is this pig asset, and that is open on the left here. And we can see that there on this line, we're looking at a payload of this file payload.usda. And that payload USDA is then loading our references of the material and the geometry right here. And so you could think of this just kind of in a hierarchy standpoint. The pig asset loads the payload loads the material and the geo. So when we see this prepend payload right here, that's basically just meaning this is the payload that we're loading. It could be named anything, but in this case, we have it named payload in order to just simplify things in our asset. We can also see here there's extents right here, which is our bounding box. That's that information, that little bit of information that can give us the shape of our asset when we unload it in the scene. So just wanted to clarify this before we jump into now the demo file. So here we are in our demo scene again, and we're in the payload section. And so we've got these two nodes. One's going to load our scene that we're going to use to talk about payloads, and the other one creates our payload scene. But first of all, I want to talk about how these two elements are being made, and that is up here in our asset building section. So if we click into this, we'll see that there's two separate assets being made. One is a pig asset. One is a rubber toy asset, and those have textures loaded onto them and some geometry. This is our component builder workflow that's in Solaris. We'll talk about this in a later course, but for now, just understand that there's a pig that's being made that has a gold shader on it, and this actually creates and manages the fact that this is a payloadable file. So this whole system creates this asset that is able to be payloaded. So when we come back over here into our create payload scene, we can see that we bring in this pig asset, and that's an orange primitive, and we can see that that's a loaded payload. And here is the toy asset, and that's a loaded payload as well. So now that tells us that both of those could be unloaded if we want to. So the next two parts of this instance, that geometry around, you can jump in here and see kind of what's going on inside of there for the instancer if you want to, but just know that this is just scattering a bunch of these objects around, and we'll talk a little bit about that later in this course. But there's a large and a small instancer, and that'll just help us see the performance difference when we're unloading these payloads. So down here, we'll save these out to disk, and then when we go up a level, we can then see our load payload scene. And I'm going to go back to the small one first, just so we don't get so overwhelmed with elements in our viewport. So here we have all these elements loaded, and the way that we can tell it to unload is by going to this mask and clicking here, and that will unload these payloads. And now you can see that there's just a gray bounding box for each element that was in the scene. And we have our pig asset, which is now kind of this reddish orange. And if we look, that's an unloaded payload. So both of these are now unloaded payloads. And that gives us a huge performance boost. So if we bring the large scene in now, we can see that we're at about 120, or we're over 120 frames a second. And if I turn this load back on, we're down to about 60, 70 frames per second. So there's definitely a performance improvement that we're getting by unloading these. And you can imagine that the more complicated your geometry becomes, the better your performance impact is going to be. So let's unload those both. And now let's say we just wanted to load in one of those sources that are being scattered. Well, we could just load the pig in, for example, and that will load all of the pigs back into the viewport. And conversely, if we load the toy asset, that's going to load all of the toys in the viewport. So let's just say we got to this point and this was maybe a more complicated scene, and we wanted to make sure that this viewer state was going to be saved into our network. Well, there's a pretty easy way to do that. We use the same dropdown and do a create configure stage node from load masks. And this will make this configure stage, and we can wire that up. And if we take this and turn everything back to the way it was, where everything's loaded in, this configure stage will now do the exact same thing. There are no viewport load masks saved. There's the load masks are saved in this configure stage node. So this is kind of the way that you can select parts of your scene to be viewed in your viewport, have optimized performance, and be able to just focus on certain parts of your scene when you're working on these payloadable USD files. Let's look at another way that we can bring in USD files from disk, and that's the stage manager. All right, so here we are in the Houdini interface, and we're going to be in the stage manager section. And so we have a few different nodes in here. One subnetwork that's going to be creating a scene that we're going to organize. This will load the scene, which we will organize. And this here, we're going to kind of build a screen from a few assets that are on disk. So as long as you've been following along with this course, you should have a USD folder here with some assets in it. And in here, we have assets that we're going to load in. So what I'm going to do is bring in this asset demo here. I'm going to bring in this pig asset, and I'm going to bring in the rubber toy asset. So this is a pretty straightforward user interface for the stage manager. We have these three different assets that we've loaded in. We can see their top level primitives here, and they're payloaded in the scene, and that's denoted here with these checkboxes. We're making sure that we're loading in the payloads. So what we can do now with these assets, which is a little different now, obviously we can't, drag these around to group them or organize them or anything like that. But in the stage manager, we can. So we could do something like taking this and putting it there, and then it's below it like this. However, that's a little messy. So let's go back here and add in a new primitive, and we'll call this one pigs, for example. And we'll take this, and we'll drop it under pigs like that. And now you can see we have a pigs group primitive, and we have 2 of our components underneath that. And we also have a rubber toy asset that's outside of that hierarchy. So that's one thing that we can do, is we can organize the hierarchy. We can also do some transform controls from this icon right here. So we could take this, and we could just kind of separate our models out a little bit, move them around, do whatever we might want to with them. And that will add some transformation data into those primitives here. So that's like the most basic level of what we can do with the stage manager. We could also do something like set one of these assets that has variants on it, which I know the asset demo has some variants set on it. We're not going to get into that right this moment, but if someone does give you an asset that you need to load in with variants described on it, we can go right here to the variants and say, okay, instead we'll do this as a squab that uses the brick shader. And now you can see that that's changed. So we can kind of control all of these things from that standpoint there, as when we're loading them in. And this, you can make as many as many primitives as you need to and group things underneath them. So these can just kind of, this hierarchy can keep going as deep as you need it for whatever you might be setting up in your scene. So that's the kind of basic understanding of what the stage manager is doing. Now, the cool thing that you can do with the stage manager is you don't have to start from scratch with it. You can actually drop down a new stage manager here, and we'll connect it into this load messy scene. So I'll load this up, and we can see here, this is kind of our basic scene, but instead everything's kind of all flattened here. There's no hierarchy going on. I mean, there's a little bit, there's some things that are grouped underneath them, but all of the top level primitives are things that we'd probably want to group differently. So now if we wire the stage manager up here, you can see that it loads in all of our primitives in our scene. So what we can do now is add in one that's maybe called geo, and we can take the ground and the sphere, and we can drop those under geo. And then maybe what we could do is add in a material like this, and we could bring in the shaders, drop those under there. We could also do a lights and grab the spotlight, the key light, HDRI, and the top light, and drag those into there. And we could always move the camera into its own place or whatever we might want to do with that. Now, render is on its own. That's kind of a top level primitive, and there's no reason we'd need to group that at all. But this shows you just how you can create a hierarchy using the Stage Manager UI. So as we're changing parameters in this user interface, what we're doing is modifying the data in the scene graph tree. So as we make changes here in the Stage Manager, that's being reflected down in our scene graph tree in the lower left of our UI. And this scene graph tree data will ultimately be what is saved to disk as USD without really any mention of these edits that we're making in this node. So that's just something to keep in mind. So in this case, the edits are stored in the Houdini HIP file and not in the USD file itself. So the Stage Manager dialog, it's a nice, simple way of doing it. It's very similar to how maybe you might be used to doing things in maybe a program like Maya or C4D, or even doing grouping in Photoshop, things like that. It's a little bit more of that drag and drop kind of UI design. So this isn't really a true procedural method like we're used to working in Houdini. There can be a lot of things upstream that'll break this, but it can be something, as you know, if you need to do something like this, like you were given a file that was incorrectly, maybe the hierarchy was not correct, you need to quickly correct it, something you could use to do that for sure. Now, another thing I just want to point out before we move on is that this UI isn't the only part of what's going on in the Stage Manager node. If we hit this show hide parameters, we can see that this is actually recording everything that's going on, kind of behind the scenes. So this is creating all of our different, change types underneath, like moving the primitives, creating primitives, doing all these different elements underneath it. Here's our translation information underneath it. So this is kind of the kind of behind the curtain view of what's going on. And in fact, I believe if we changed this to none or to scope, it would change the way that these parent primitives are being created. So something to keep in mind, that you can get to this information behind, kind of behind the scenes, behind this UI. So that's kind of an overview of how the Stage Manager works. And it's something that you can certainly use to be able to kind of rearrange your scene and make sure your hierarchy and your objects are coming in the way you want them to. Now let's take a look at the primitive LOP, which is a node that allows us to create a primitive hierarchy or multiple hierarchies using path strings. So here we are in Houdini, and we're looking at the primitive LOP section of our demo scene. And in here, we just have a primitive node. And by default, this will just make one single primitive, and it'll be named to $OS, or the name of our node. So from this paths parameter box, we can set a whole bunch of different primitives and parents, and I'll show you real quick how we can do that. So let's say here we do parent and then primitive like this. And now you can see that we've created a parent primitive and our leaf primitive that we've just called primitive. So what we could do is maybe name this something a little bit better, something like mesh, and maybe here we can say /parent/light. And here we can do parent/ camera. So now we have kind of a hierarchy being built here where we've got a parent and we've got our camera, light, and mesh primitives. Now, sometimes you'll hear the term namespace used, and that's basically just describing this set of paths that that gives the identity for the primitives on a stage. And a path is just a location in that namespace. So if you hear that used, often that's used in the official Pixar documentation, but just know that that's kind of the set of paths, and it has a root that is represented by a /. So this is kind of the way that this whole primitive node works, is that we have these different paths, and we can make as many as we need to in there to create as many primitives as we'd might like. So this could be really useful if you're creating kind of a skeleton hierarchy for a scene or for a shot, or if you're just wanting to build a few of the same type of primitives at the same time. So let's kind of take a look at how the rest of the parameters in this work and how we can use those to kind of affect this hierarchy that we're building. So up here we've got the primitive kind, and from here we can set this to something like a component, which would make these all assets like we might have if we're working with something from the asset building, the component building workflow that we have. Here we have group, which would set these all to be group primitives, or we could set them all to be assembly primitives. And basically, as I've said before, these kind of go up in the coarseness of how they would be in the scene. So a component might be built up of multiple subcomponents, a group would be built up of multiple components, an assembly would be built up of multiple groups. So for right now, I'm just going to set this to none. We don't really need to worry too much about that. Here we could set the parent primitive type, so we could say none for the parent or scope for the parent. I'll keep that at XForm because that should have some maybe transform data on it. The next thing down we can get to here is, say, the primitive type. And here we have a whole list of types. Now, I'm not going to go through every single type here or anything like that, but just know that this is a great place you could come to find, a list of primitive types if you wanted to really quickly while you're in Houdini. And if we selected something, say, camera, for example, now, all of these leaf, or the lowest part of our hierarchy, these primitives will now all be cameras. So what I could do maybe instead is say something like cam1, and then here I could make this camera 2, and then maybe cam3. And now we have maybe something that would group our cameras together in our scene and allows us to kind of quickly create a bunch of cameras. I should actually set my display flag here so we can see that sure enough, this is a camera that we're building. So now just to clarify, when we're setting the parent primitive type, that is setting anything that isn't a leaf primitive in our hierarchy to that type. So in this case, it's just the parent primitive that is getting the type from that dropdown. When we set the primitive type proper, we're setting the type for the leaf primitives in that hierarchy. So in this case, it's our cameras. So just something to make sure that you understand the difference between the parent primitive type and the standard primitive type. So if we wanted to maybe make another section, what we could do is we could add another primitive into here and wire that in. And here again, this will start with $OS, so this would be primitive 1. But let's change this to say lights / and then what I'm actually going to do is maybe say disk light 1 and then copy this whole thing a few times, and I'll do 2 and then 3, and down here under what type we want to use, I'll just change this to disk light. And now you can see we have lights, and here up at the top I'm going to change this to maybe cameras, and I'll just copy and paste that down just to make this a little cleaner so we can see exactly what's going on here. So we've got cameras and we've got our lights, just like that. So this is a, kind of a quick way that you could build up a bunch of different primitives of the same type, or create a hierarchy of kind of skeleton primitives that will be loaded later on in our USD workflow. So the last part of this is the specifier. And this is something that's a little bit maybe not super obvious from, looking at it from the outside, but there's 3 different things that we can do here. The first one is define, which basically just says to create this kind of concrete primitive. So we're defining this as a disk light. It is a disk light. There's nothing, just make a disk light, put it in there. This is a camera, make 3 cameras, put it in the scene. So that's what define is. That's kind of the most basic way of making a primitive. Now over is a little different, and you can see here that I'm setting this on the lights primitive 1 here. And so I'm just going to call these lights and cameras just to kind of make sure those are specific. And here we can see that it's added this new icon into our scene graph tree. And basically what the over is an override that's coming into our USD hierarchy, into our USD scene graph. And so if we were to maybe place this lights primitive on top of another lights primitive, this would be an override that we might do to something down the line. So that's what an override or an over is. And class is kind of the last one. And this you can see has changed that icon again. In fact, it even jumped it up to the top here. And this class primitive basically is one from which other primitives inherit their attributes or inherit their, their states, their shaders, things like that. So, this will be something we get into later in this learning path, but just know that these different specifiers kind of have their own, each have their own unique way of kind of making a primitive into the USD scene. So hopefully that makes sense, and that can give you an idea for how you could build in something like a hierarchy, or even start to kind of group and set up your scene from scratch using just this primitive node. So the XForm and Transform LOPs are very similar in function and name, but they have a couple of really unique differences that we're going to highlight in this chapter. So here we are in the demo file, and we have this section XForm versus Transform LOP. And really all we're going to do here is bring in a simple scene. Right here we're going to be sublayering in a simple scene. You can see the hierarchy is pretty well defined. We've got all the same things we had before, shaders, lights, geometry, cameras, things like that. So this Transform LOP and the XForm LOP sound very similar in name, obviously. We want to talk a little bit about how these are different. So if we go to Transform, that's where that would come from. And if we do XForm, there's 2 different here, but those are basically the same node, just set in a different parameter. So this is a Transform LOP here, and this is a Create XForm LOP. So The Transform LOP does exactly what you'd expect it to do. You can set it to bring in some primitives and then do some transformation on it. It's really not a whole lot more than that. And we can set the primitives any number of ways. We can use our little dialog here and maybe just grab our geometry, hit apply. And now if we start transforming things, those will move around. It's pretty straightforward. There's not a lot of difference there. Now, when we come over here to the Create XForm LOP, this is a little different because it has the ability to not only transform stuff, but also to create an empty transform primitive. So, or an XForm primitive, if you would. So here you can see we have a Create XForm LOP, and that's coming right from the name here of this node. So we could say, we could just call this maybe new primitive. And there it's going to get put into our scene graph tree right there. And as well, we could obviously parent this underneath something. We could just call this parent like this, and that would throw it under another parent primitive. And we have all of the same things that we can do here. We can set these to be what kind. We can specify, give it a specifier, and we can say what the parent is going to be as well. And so we can do a whole bunch of, simple creation here with this one node, but we can also, I'm just going to set this back to where it was, and we can also change the action here to edit. And once it gets into edit, you can see that the interface just changed a lot. And really at this point now, it is a transform node. So we could do the exact same thing we did before. We could drag and drop our geo in here. We could then use our interface here to just kind of move stuff around. We could, change it in over here. So these two nodes are very similar, but the real difference here is that the XForm node allows you to create new primitives if you wanted to, whereas the transform node doesn't. So hopefully that'll clear up any confusion you might come across as you're maybe dropping those nodes down into your scene in Solaris. Now, USD doesn't have the concept of groups or point, poly, edge selections or sets or anything like that that you might find in other software. So how do we link things like materials to portions of our geometry? All right, so we're in the geometry subset via groups portion of the demo file. And let's take a look at the node that's in here. So we have this load geo groups SOP create node. And we can see that this is bringing in some geometry, and there's some primitives being created in here. And actually, we already have some geometry subsets created. So let's just dive in here real quick and see what's happening here. So we've got a test geometry, and it has some attributes on it. It also has primitive groups, which are basically just like selections that you can save on your geometry that kind of move along with it through the network. So we have groups, we have attributes, and what we want to do is we want to take these groups and turn those into the geometry subsets. Right now we can see this is making these subsets from a path for our material. We don't really want that to happen. So let's clean this up first. And what we can do is we can take this SOP create node, scroll down here, and turn off this partition attributes, which is on by default for shop material path. We don't really need that. So let's come down here and we can turn on subset groups. So now we can look at those groups that are in or that are written on that geometry in the SOP create node and select some. So we could select the body, we could select the eyes, select the pants, and you can see that those get added in here onto our mesh. But if we wanted all of them to come in, say we had a whole huge group of them or a huge list of them, we can just use the star wildcard, which will bring in all of our groups that are on our geometry. And you can see here now that we have the body, the eyes, pants, all this kind of stuff. And now those can be used as primitive selections in our Solaris interface so that we can then do things like attach materials to them or anything else that isn't a transformation data, because we can't actually use this to transform. This is a way to split our geometry up, but it isn't a way to set like a transform. So if we took something like the tank top here, tried to transform it, this is not a separate mesh. Everything is staying put. So if you wanted to use a separate mesh for each of your objects in your scene, you'd need something like a name attribute or a path attribute. And we can see that up here we have these different path attributes that we can use to split up our geometry. So in this case, we're just looking at the geometry subset, and we can use those groups in order to kind of break up our geometry and have these almost like selections that we can use within our USD scene to attach different things to our mesh. So now what if we had something other than groups that were defined on our incoming geometry? How could we make geometry subsets from those? Well, let's jump into Houdini and take a look. So here we are in our demo file, and we're looking at the geometry subset via attributes section. So we have a very similar thing to what we looked at in the last chapter, which is a SOP create node. And let's go inside of it and see what's in here. So there's the test geometry. There's an attribute wrangle, which is just some code that's basically going to make a shader name attribute. So we're making our shader into a name attribute basically. And then this name from groups we're going to use that in a second to see how we can split our geometry up a little bit differently as well. So here, this is kind of loading in almost exactly the same as it was previously. We have our load geo attributes, primitive, we have a mesh, and then we have two geometry subsets based on the shop material path. So let's remove shop material path, and let's grab our shader name. We can see it right here in the drop down. We can use shader name. So here we've got shader name, principled shader body, shader name, principled shader close. And so if we wanted to maybe make this a little shorter, we could actually check this box and turn off prefix subsets with attribute name. That brings it just to principled shader body, principled shader close. So that is kind of one way that we can use this attribute to kind of split up our geometry subset. But let's go back inside here and let's turn this name from groups back on, and you'll instantly see that something has really happened over here quite dramatically. We now have a bunch of different meshes, and underneath each of these, we'll see that there's a different principled shader geometry subset beneath those. And so the reason for that is that we've now created a name attribute for each of these distinct geometry pieces here. And that every time you have a new name or path attribute in Solaris, you can see right here, this path attribute is looking for either one of those. And so that'll split your mesh up into separate pieces or separate meshes. And then you can have geometry subsets below those. So if I was to remove this name attribute here, that would keep our single mesh just the way it was. It wouldn't look for that name attribute at all. And what I could do as well here is I could actually add in shader name, and that would actually split this based on the shader name. And I could come down here and partition it based on name down here. So there's several different ways that we could split these geometries up. And whenever you have a mesh, just remember that you can actually transform that. So we could either transform, in this case, the close or the body. So these are different ways that you can kind of split your geometry when you're bringing it from SOP level Houdini geometry into Solaris and creating USD geometry and hierarchy. So hopefully that makes you aware of some of the ways that you can kind of control that geometry as it comes into USD. All right, so let's take a quick break from the Solaris interface and talk a little bit about a concept called schemas. So schemas are basically the same thing as a type on a primitive. And if you remember from when we talked about this previously in the last course, the examples of types are things like meshes, lights, cameras, shaders. Pretty much it defines these objects that exist in USD. And so schema and type are kind of go hand in hand a little bit, but a schema basically also gives us some definition to how the properties are kind of brought from one application and into USD and vice versa. So this is a way to basically define everything that happens when you're making, say, a camera or a mesh in USD. So one of the main things that happens there is attribute renaming. So common attributes in a software like Houdini actually get renamed to the corresponding type of attribute that would exist in USD. So for example, here's four really concrete, very common examples. So P from Houdini will get transferred into the points attribute in USD, and N gets transferred to normals, V gets transferred to velocities, and UV is mapped to ST. So these are some recognizable examples when you're working in Houdini, but there's obviously going to be these same things if you're working in another software. So I'm sure there's information, you can look to those, but just know that if you're looking for something to tell you how these things are getting, renamed and remapped, schemas is kind of a place to look to understand, maybe in another software package, what points is going to get mapped to, or the normals, or anything like that. So just something to keep in mind. And then if you have properties that are not, defined in that schema, those are going to get saved as primvars. So these are very similar to the concept of just any attribute in Houdini. They basically map to a primvar. So here's a pretty common example that would happen in, an attribute from Houdini, which is shop material path. That gets mapped to primvars shop material path. So this is kind of the catch-all for anything that isn't specifically defined in the schema. So something like a point or a velocity, those will be defined and renamed, but anything that doesn't fall into that will get this primvars added to the front of it. The only one that I listed that doesn't get that done is UV to ST. ST actually has primvars in front of it as well. So let's take a quick look at how this works in action in Solaris. All right, so I've split up my viewport a little bit just so we can see both our geometry spreadsheet and our scene graph details at the same time, just to analyze what's going on in the SOP context and in the LOP context at the same time. So let's jump into this SOP create node that's in the schemas section of our example file. So let's go into here, and we'll see that we're just basically putting some attributes on a four-sided polygon. Nothing really too exciting going on here. So first of all, we have point positions, and as we come down here, we can see that P in here has been turned into points, and we can see the point values there as well that match up. So then next, we add normals onto our grid, and you can see here the attributes that have been added are under our vertex. Here are the normal attributes that have been added. And if we come down here, we can see that this is called N, and here it is called normals, and these attributes should match up exactly. Sure enough, they do. The next node down will add in some point velocity. I just added some random noise, and this is going to be a point attribute. So let's go back up here, and we can see now that this should add velocities. So if we look here, we have velocities, and that matches up with our V attribute. See the values here and here match. Then I used a UV project just to make an orthogonal projection of UV attributes, which is basically very simple, and just setting that to 0 to 1, basically. So we can either have this set as a point or a vertice. And so either way, it comes in here, gets renamed to primvars ST. We can see the attribute here, and that matches up with this as well. Now, it doesn't pull in the third component of that, because most of the time you're not using that with UV coordinates. You're just using your two-dimensional coordinates, so they make that assumption for you. So just know that if you wanted a third attribute in there for some reason, you would just need to check that as, you need to change this to UVW, so it doesn't try to read it as just a two float. And then I also added a shader onto this here, just from a material network. There's a shader in here, just a basic shader that's got some color. And I assigned it to the material here, and that creates our shop material path. And once we bring that over to Solaris into the USD context, we see our shop material path right here, and it adds that path into the value. So hopefully this gives you kind of a concrete example of how we bring things into our Solaris/USD world, and how those either will get conformed to new names based on the schema, or they'll get the primvars added. And we'll see in the coming chapters how we kind of build on this information and start working with even more primvars as we set up our geometry. Let's now talk about how extra attributes that aren't defined in a schema are brought into Solaris and USD and saved out as primvars. So here we are back in the Solaris interface. We're looking at our demo file here in the primvars section. And in this, we just have one node, and we're going to use that to kind of see how these geometry attributes come into Solaris and get written to USD. So let's jump in here first and take a look. We have a pig head geometry in here, just adding some normals, bringing it up to the ground plane, and subdividing it just to give it a little bit more points to add some attributes to. Here, we're giving it a weight attribute. So if I go into here, right click, I can see my weight attribute there. And then we can go down. Next, there's a vector attribute here. This first one was obviously a float attribute. This next one is a vector attribute, and this might be, you know, the direction of some effect that you're doing. So there we can see we've got a whole bunch of vectors. We can visualize those. And then down here, just promoting UV up to a point attribute, just so I can use that to drive some noise. And here we can see that there is a integer attribute level, which is set between 0 and 5. So there's 5 different levels here that are being written as integer attributes. So those are all of our different custom attributes that we're going to be writing out here. And in fact, we'll even have this point UV that's going to come into our geometry in Solaris as well. So we can kind of see how a point UV versus a vertex UV would come in differently. So let's jump up here, and we'll go over to our scene graph tree, and we'll select the mesh, and I'm just going to kind of make sure that this is maximized so we can read it. So in our scene graph details pane is where we're going to be able to see all those attributes. So first of all, we can see that our points have been converted here. Our positions have been converted to this points, and our normals are under the attribute of normals here. And and obviously that was N, capital N in regular, you know, SOP world, and it was capital P for the point positions, and that's been changed to points. So now if we scroll down a little bit here, we can see all of the different primvars. And these attributes are all going to be basically the exact same attributes that we had in the SOP create node. These are just getting transferred right over. And here we can see we get, for the values, we get what point number it is in this case, and then what the value is. And as we go up here, we can see, you know, this is our ST that has been converted from our standard vertex UV attribute, and thus gets renamed to this ST. And here Primvars point UV, this comes in as a 3 float vector as opposed to a 2 float. Because UV, it's kind of expecting it to not be a UVW map, it's just expecting it to be a UV map. So that converts it to a 2 float vector. And this is a 3 float vector here. So then we have our level, which is an integer, and this you can see here we're getting all integer attributes. And then we've got our effects direction, which, you know, gives us these vectors and all these different you know, directions and things like that. So that kind of gives you a sense of how these primvars are written in here, and also a little bit of how the standard attributes that come from our geometry are converted once they come into the Solaris interface, and it'll just give you an understanding of where to find maybe your custom attributes that you're writing onto your geometry before you when you bring it in. In this chapter, we're going to look at how to take objects and elements that we've created in the Solaris interface in the LOPs context and move that back into Houdini's SOP geometry context. All right, so in our example file here, we're in the LOPs to SOPs section, and you can see here that there's a subnetwork that's got some elements inside of it, and we're calling this SOP load scene. We're not really going to do a whole lot with it in Solaris here because we're going to actually go back over to our object context. But let's first go inside and see what we're doing in here. So we have a pig asset that we've saved out previously and a toy asset. Those are both loaded in. Then we use an instancer to kind of move these around. We're not going to talk exactly about how that works right now, but this basically makes a bunch of copies. And then we have a camera that we've loaded in here as well, and an out null that's basically a place that we're going to point to load these back in as geometry. So you can see here we've created a bunch of primitives named either pig or toy, and they're numbered based on you know, how many there are of each. And obviously there's cameras, an XForm right here, and then the Solaris cameras underneath it. So let's go back up here and switch over to our object context. And we can see here, there's a section that's talking about the exact same thing we're doing here, LOPs back to SOPs. And there is two different nodes here. First, we'll just touch on the real simple one, which is the LOP import camera. So this node will allow us to load our camera in from Solaris. So if we look at this here, we can kind of see that there's our camera. It's in the exact same orientation in our scene. So if we animated a camera in Solaris, we could bring it back in here into our SOP world and say we're doing some sort of animation or effect or something like that. We could see it from that angle or that perspective. So it's really simple to make this work. Basically, we look at the SOP or the LOP path here. We just point to it, which is right here, that out null that we created. And then the primitive path, we can use this little arrow selector, and we can just make sure we're selecting this primitive here, which obviously is the camera primitive. And everything else really gets kind of calculated from those locations that we're pointing it to. So it pulls in all of the resolution and focal length and all that kind of stuff from it. And same thing with f-stop, shutter, focus distance, things like that. So that's kind of an all-in-one camera loading object here in our SOPs context. So this geometry node here is going to load in obviously the geometry from our LOPs, and let's go inside and we'll see what's in there. There's a LOP import. So this LOP import node is doing most of the kind of the work to bring stuff into our scene here. You can see that this is very similar to the way that the camera SOP worked, where we were basically importing that. This here, we're just pointing to the same out null, and we're looking at the instance or small primitive. So we can just select this here and make sure we're selected on that. And you can see that this is the primitive that we're going to look at. And then from there, we can pull in all of this information, all these child primitives below it. Let's take a look at the geometry spreadsheet here so we can see kind of exactly what's going on here. So at this point, in this point of our network here, we can see that we have one point, one primitive that's coming in, instance or small, and that's really about it. Everything is kind of loaded into this one point, one primitive. If we select here, you can see that we have one of everything, and it's a packed USD. So all of the USD information is basically loaded into that one point, and that's really the only edit that we can do to it is adjust that point, maybe its rotation, things like that. So this all is coming in as one big, huge asset that we'd have to kind of work all at the same time. This really isn't separate things yet. So there's a couple ways that we can make that work here. So the first thing we need to kind of fix here is I'm noticing that this is coming in as animated geometry here. So let's go up here to time sample and set this to static. That's just going to make sure that when you're bringing something in, you're not having it recook every frame because this doesn't really need to. This is just a static import of a scene. There's no reason to have animation there. And also we're bringing in a few other attributes down here, things like path and the name attribute. So this is all pretty standard stuff that we're bringing in from LOPs. So let's go down here and take a look at this unpack USD to components. That's what I labeled it. So this is an unpack USD SOP. And what this is going to do is break our geometry out into the individual components that are listed here. You can see these are all components here. And the way that we define this in this node is through this concept called traversal. And what that means is it's going to look through this scene graph tree and go down each one by one through these branches and stop and kind of end its traversal, end its search when it gets to components. So each branch, it's going to stop at a component. So here it gets to pig, it stops, it says, okay, that's what we're going to load. Here it gets to pig 1, sees that that's a component, and we load that. So that is what's happening here. And you can look and see that sure enough, we're not getting prototypes because that's not a component, but we are getting pig 1, 2, 3, all the way down, all the toys, everything like that. And those are bringing in points as well. So now when we look at this, we see we have 56 packed USDs. So this is the same type of geometry. It's all packed into one point, one primitive, one vertex per primitive that's coming in here from the scene graph. But now we could actually take these elements and move them around individually. So if we were actually trying to select these elements, we can now see that they're all kind of separate, and we can select them and move them around as needed. So that's a little bit of a different way of doing it, bringing in by the components. We can also look at this and say, okay, we don't want to have it traverse based on the components. Let's do it based on these G prims, which are basically all the way down inside of this render, and it's the shape that we're looking at now. This is kind of the leaf primitive, more or less, or this kind of really low level primitive that's inside of here. And so now you can see that these have all been changed to just say shape. Now this doesn't give us quite the same information that something like bringing in the component does, because everything's named the same. It doesn't really tell us too much about it, but you can see we can select these all separately and get them all these all are separate objects as well, and we have 56 packed USD still. So there's several different ways that you could do it here. You could also do groups, but that's going to traverse this stage and only find this prototypes primitive, which really is just kind of there to say, hey, what are we loading this from? It doesn't actually hold the geometries per se. It doesn't like resolve to any geometry. So this we'll learn about more later, but this doesn't do anything because there's nothing really to load there. So groups isn't very helpful here. And no traversal just means it's not even going to look through this. It's just basically not loading anything from it. So so this components really in this case is the best thing that we want to do in this kind of solution. But you might be wondering then, how do you get actual polygons, points that you can edit from this? Well, right now, this one is just outputting packed primitives, which is that concept that we're seeing here with these packed USDs. If we go over to this side here, unpacked polygons, it's the same node, but instead this output has been changed to polygons from packed primitives. We're still looking at the traversal being components, and so we're still getting that, but we're unpacking that geometry now. So now this is individual polygons. So if you look here, and you can see that I could select individual polygons on these. And that's going to be a little bit of a different workflow that you might need that for. Another thing you might notice here is that these have their original test geometry shading. The pig and the toy have shading that comes with them by default. And if you remember in Solaris, we had these as like kind of chromy colored things just so we could see that there's some materials on them. But in here, we're seeing their original kind of standard Houdini shading. And that is because we've unpacked this shop material path. And in SOPs, it's smart enough to find this path, find these original shaders, because it's still in this HIP file in our Houdini session. It can find that and load it in. So it knows right where to look for that material path to be able to load that back in. So that in this situation is maybe a little bit of an odd part of it, that it's bringing back that original shading, but might be useful if you're doing something where you're not seeing your shading maybe by default in Solaris, and now you can bring it back in here and see that while you're working. So that's just something to be aware of, basically, that all of your attributes become unpacked. You can see that we've got all these different path and names that have been written here, and any point attributes like normals and things like that come back as well. So hopefully this gives you a good sense of if you wanted to bring something back in Houdini, whether it's in the object context, whether it's in a SOP network that's right next to your geometry and your scene in Solaris, or even in some sort of a SOP create node or something like that, you can always use this LOP import node to bring things in and start editing them back at their point and primitive kind of level.